Hey everyone. While I'm out, I'm gonna introduce a new-ish idea, but it just builds on what we've been doing in class together recently, so it shouldn't feel overwhelming. And then when we get back, we'll talk about kind of one more integral technique, and then we're gonna deviate to our last unit, which kind of ties together integrals and derivatives in an interesting way. So basically, we're going to use the disk method again. It's just rather than revolving around the x or y axis, we're going to revolve around a different axis, meaning a vertical line or a horizontal line that lies somewhere else. So if we look at example one, I'm giving you a function, I'm giving you a line, and so here's our f of x, here's our y equals 4 horizontal line. So in other words, because it's a horizontal line, we're going to treat it like an x-axis. So if you treat it like an x-axis, basically we know we want our area function in terms of x. All right. So normally I would say, okay, here's my function. I would find the piece, and then I would just imagine revolving around the x-axis. So all I would have to worry about is we're creating a circular cross section. So I'd use pi r squared, and then I would just simply plug in the function for the radius. But because I'm not worried about under the function, I'm actually worried about above the function. I'm actually looking for a radius that captures this section here. So if you imagine me rotating, essentially it's going to create this, and we're going to take our cross sections essentially going to do this. And so I'm building a bunch of circles here. So if you need to imagine that, I can imagine, oh, here's another circular cross section, and so on. All right. So the way I would find this is rather than simply using the function, this length here is actually the difference between the line I'm rotating around and the function itself. So in other words, this radius here is really 4 minus x squared plus 4x plus 4. That's the only thing. So when the axis I'm rotating around moves above, I have to find the difference. So that means this function here is really going to be pi times 4 minus x squared plus 4x plus 4 squared. And now I can use it to calculate the volume. One thing I would note here is this kind of sets you up for quite a few errors where this isn't a hard thing to simplify. So I could really, if I did 4 minus all of this, my 4's would end up canceling. And that would leave me with a negative x squared minus 4x squared, which is a lot easier to end up plugging into my calculator. Sorry, the camera is freaking out. All right, so if that's true, all I have to do then to calculate my volume is, like we did in class last time, I'm going to pull my pi out in front and just say negative x squared minus 4x squared dx. And then nothing changes with my bounds because it's in terms of x. I see I'm going from negative 4 to 0. And so there's my volume equation. All right. If I punch that into my calculator, I'm assuming everybody's good with this, but just in case, remember math button, option 9, we're going from negative 4 to 0. And should have inserted my pi. All right, so the key here is because we have it in parentheses, don't forget to insert your own parentheses here, as I did. All right, and then this way, we're not losing that exponent. So I know a lot of us ran into that issue last time. So now if I hit enter, there is what I get as an approximation. All right. However, notice how I put the pi in front. So if I wanted the decimal solution, I get 107.233. But my preference would be, as we talked about last time, is use the function, but leave pi out of your calculation. And you get that 34 and a third. And if I hit math, fraction, that tells me 512 fifteenths is my fraction. And so the way I'd prefer that you write this is 512 fifteenths pi. Then you can't get flagged for putting the inappropriate number of decimal places on. All right, and that's it. So that's how we rotate around. All right. The other case you might run into is where rather than rotating around a horizontal line, we're rotating around a vertical line. In this case, our vertical line ends up being x equals pi over 2. And our function here is y equals sine x. But because we're creating our cross sections in this direction, just remember I need to rethink my function as x equals rather than y equals. So all I would do is inverse sine both sides. So my function in terms of y is really inverse sine y is equal to x. All right. So we're doing around a vertical line. So I know I'm going to have a of y. And just like before, you can say, because it's a vertical line, we're going to treat like it's a y-axis. That's why I'm saying it has to be area in terms of y. But because we're revolving, it's still going to be a circular cross-section. And now it's up to me to say, once again, if I was revolving around the y-axis, all I would have to do is put the function in for the radius. But because I'm actually finding the gap between a larger function and another function, I have to find the difference. So in other words, this radius is pi over 2 because that's my larger function minus this function. But once again, because I'm doing a cross-section this way, I'm rethinking about that function in terms of y. So a of y is really just going to be pi times pi over 2 minus inverse sine y squared. All right. And now when I want the volume, same thing, I'm just going to pull that pi out in front. I see, because I'm doing vertical cross sections, that I'm really going from 0 to 1. So I'll have 0 to 1, and then I'll have my pi over 2 minus inverse sine y squared dy. All right, this is one that's not really necessarily nice to simplify. And so if I just punch all of this into the calculator, I'll just get 3.586. So I'll give people a second to confirm that I am in fact right. You would get 1.141 pi. All right, so either of those are acceptable, but because this is a decimal, I would just go with this. All right, so that's kind of the gist of how we do this stuff. I'm going to have you give this a shot today, and then if you have any questions, I'll obviously address them when I see you guys again on Tuesday. So have a good day today, and I'll see you next week.